Hi there! Welcome to the 18th episode of the Synth project, where we are going to build a synth together. So far we have built a VCO and a controller for a softpot interface. Next obvious move is to work on the keyboard and its interface. However, before doing so, I would like to add another module to the synth, which will allow us to experiment with more features once we have the keyboard available. Not to mention that we can use it right away with the softpot interface. The module I would like to introduce today is the LFO, or Low Frequency Oscillator. This module works like a regular VCO, but it is capable of emitting frequencies in the subsonic range, down to periods of several seconds. The output of the LFO can be used as a control voltage for several other elements of the synth. For example, we can use it to modulate the frequency of the VCO signal to obtain a vibrato effect, or we can use it in conjunction with a VCA to obtain effects like the tremolo and the Leslie. There are actually several ways to use an LFO, and that's why I thought to build it right away, because it will make the use of the softpot and the keyboard even more pleasurable. And so, with no further ado, let's dive into the design, prototyping and realization of such a module. Enjoy the video! Rather than using a ready-made integrated circuit which is full of options we don't really need, I decided to design a circuit made out of simple op-amps. Well, and some transistors too. The circuit is divided in three different blocks: the oscillator itself, which provides simultaneously the triangular and square shapes, and two separate shapers, the first one that takes at its input the triangular shape and modifies it into a sine shape, and the second one takes both the triangular shape and the rectangular shape to create a ramp and a sawtooth. Let's examine these three blocks one by one and also test each one of them in lab. Here is the schematic of the basic oscillator, which is built around the op-amps U2.3 and U2.4. The control voltage is provided through U2.1 and U2.2, while the outputs are buffered by U1.1 and U1.2. The control voltage may come either from potentiometer RP1 or from an external source through the connector J2. RP1 provides a voltage between ground and plus 12 volts just by adjusting its cursor. The two sources can act independently or can be mixed together to create a more specific range of frequencies. U2.1 acts as a mixer using resistor R3 and R8 for the inputs and resistor R1 to set the total gain of the stage to -1, since this kind of mixer inverts the input signal. But since we need a positive control voltage and not a negative one, we use an extra op-amp to invert a second time the signal to make it a positive signal. Such op-amp is U2.2, which is also set with a gain of -1 through resistors R5 and R2. Remember, the gain of an op-amp in an inverting amplifier configuration is given by the ratio of the negative feedback resistor and the input resistor. The oscillator itself is made, as mentioned already, by U2.3 and U2.4. The oscillation frequency depends on the input voltage coming from U2.2 pin 7 and the capacity of C3. When such input voltage is applied to pin 9 through resistor R6 and to pin 10 through the voltage divider made of R9 and R10, capacitor C3 starts charging, and the higher is the control voltage, the faster C3 charges. This makes the voltage at pin 9 increase linearly, while voltage at pin 8 decreases linearly, at the same pace, of course. The voltage at pin 14 is currently a steady low, since voltage at pin 13 is more negative than pin 13. Once the voltage on pin 8 and pin 13 goes below the voltage at pin 12, pin 14 goes finally high, and transistor Q1 switches on, causing a steady discharge of C3. Now the voltage on pin 9 starts decreasing linearly, and the voltage on pin 8 increases linearly at the same pace. As soon as the voltage on pin 8 and pin 13 become higher than the voltage on pin 12, pin 14 goes low again and transistor Q1 switches off. At this point, C3 starts charging again and the cycle restarts from the beginning. You can see now how the voltage at pin 14 has a square shape, while the voltage at pin 8 and 13 has a triangular shape. These voltages, to avoid overloading the oscillator, are applied to the two voltage followers made out of U1.1 and U1.2, and we can extract the two signals from their outputs. Let's now move to the lab to see how this circuit works in reality. Here is the oscillator circuit mounted on the breadboard. Here is the TL074, which contains 4 op-amps, and here is the transistor that helps this chip to do the oscillations and form the square and triangular waves. This one instead is the LM358, which has 2 op-amps that are capable of providing the impedance adjustments for the outputs. Here is a potentiometer for controlling the frequency of the system. So now let's power it up and let's see how it works. Let's connect here the probe from the oscilloscope, and let's take a look at the oscilloscope now. So this is our triangular wave, and right now the potentiometer is all the way to the left. There is not much we can see from here, but let me adjust the time base of the oscilloscope so you can see actually what is going on. I'm putting it to 800 milliseconds, that should be enough. Let's increase a little bit the potentiometer here. Now you can see the wave being generated, and you can see how there is a triangular shape right over here. Let's wait a little bit to see better what's going on. See, it's very slow, it takes several seconds to complete. So this is 2 seconds per division. So if we want to see how is the period of this of such a wave, we can count over here. This is 1, 2, 3, 4, 5, 6.5 squares, which means it's about 13 seconds, the period of this wave. It's very slow, as you can see, but now we can increase the frequency through the potentiometer. Let me do that. I'm putting to the maximum, and let me expand now the scale so you can see it. Here it is, and this is a 14 Hz signal. So still very low, but this is the maximum frequency this circuit, the way it's configured, can handle. Now let's switch to the square wave, so you can see that one too. There it is. It's pretty good, I would say, and the frequency is the same, 14 Hz. Now let me slow it down. Let's see if we can go to the minimum we already observed for the other one. Let me increase the sweep time. Set again to 2 seconds. We can go lower, of course. I'm keeping adjusting the potentiometer so you can see what happened while I'm changing it. Okay, I guess this is enough for this system. Now let's go back to the schematics and see how we can make the sine wave. The sine shaper is based on an overdriven differential amplifier made out of 2 NPN transistors, Q2 and Q3. There is a lot of math behind this schematic involving trigonometry and calculus. In my case I just reused a known concept for this project with only slightly changes. But if you are interested in the math details, I suggest you to refer to the bibliography I added to the description below. Let's just say for now that Robert Moog itself worked on perfecting this configuration. One important thing to note is that the differential amplifier is very sensitive to parametric differences between the two transistors. It is therefore important to select two transistors that have a beta and a VB as close as possible to each other, let's say within 1%. You will need to get a bunch of BC547 and measure yourself these parameters until you find the right pair. To take these measurements, I used this simple and cheap device that I found on Amazon. You don't need anything particularly sophisticated for these measurements. I also added a link in the description so you can eventually buy it for yourself if you don't have any other way to measure beta and VBE. In addition to selecting two almost identical transistors, you also have to make sure that their temperature don't drift apart. To prevent that, it is wise to attach the body of the two transistors to each other with some thermal tape, or at least glue them together. You'll see what I mean when we go to the lab to test this circuit. Another approach would be to use one of those already coupled transistors available in the same container, and therefore already thermally coupled. One of these devices could be used in place of the pair of BC547. The principle used for this shaper is to use the transistors in a region of their characteristics that is not linear, to use the nonlinearity to transform the triangular shape in input to the circuit into a sine shape. Basically, the differential amplifier, coupled with the op-amp U3.1, will work as an amplifier with variable gain, and the gain decreases with the increase of the input signal. U3.2 is used, like in the previous schematic, in a voltage follower configuration to reduce the output impedance of the circuit and to avoid disturbing the actual shaper. And now let's move to the lab to see how I assembled this circuit and how it works. And here is the breadboard where I built the sine shaper. We have just one IC, which is a LM358 with two op-amps in it. And then we have these two transistors, and let me zoom in so you can see exactly what's going on over there. These two transistors are connected back to back, and they are taped to each other so they cannot move. And this is thermal tape, so it will help distribute the heat generated from one transistor to the other, so that they basically have about the same temperature. And this is very important, as we explained already when describing the schematic, to make sure that the sine wave has symmetrical shape. These are the two controls for the system, and the output is right over here and as a sine wave. So let's check it out. Let's connect it to the other oscillator now, and let's see how it works. So first of all, we connect the power supply. I'm gonna connect all the pieces from one blade to the other. So this goes over here, and this one goes over here, and we connect also the other side, this with this and this. With this. And now we have to connect the triangular wave output from this point in the middle directly to the input of this other system, so we can basically use it as a base for creating the sine wave. And to do that, so we have to go on the pin right over here, there, and on this other side we have to go to pin here, right here. There we go. This should allow us to have everything in place correctly. So let's power it up one more time, and this time I'm gonna put the probe of the oscilloscope right over here, So we can see the sine wave being generated, being actually shaped from the triangular wave. So let's go again to the oscilloscope, and you can see the wave right over here. And of course the frequency of this one will be the same as the triangular wave. This is just a basic changing of the shape. Now let me show you how those two twin pots work. So let's go back over here. I'm gonna show you first what this twin pot does and then the other one. So if I move the first twin pot I told you, you can see what happened here. The shape tends to change and becomes triangular again. So basically this twin pot is used to adjust the shape of the wave until we reach the perfect sine wave. And then the other one instead, you see this impacts the symmetry of the wave. So let's increase the frequency a little bit so I can adjust it properly. Shortening here. So first let me adjust the symmetry one more time. Okay, and then the shape with the other twin pot. Okay, this should be kind of good. One thing we can do is just move to the frequency domain, and here you can see there is this spike here, which is the base frequency of the sine wave, and then there is a little bit here because of course this is not a perfect sine wave, but it's good enough for our purposes. Back to the shape, and here it is. And now let's go back to the desk and let's take a look at how we can create the shapes for the ramp and for the sawtooth. And here finally is the last block, the ramp and sawtooth shaper. This module takes as input both the signals generated by the basic oscillator, the triangular shape on point A and the square shape on point B. These signals are not taken from the actual output of the basic oscillator, but from the points where they are actually generated, and that's because we need them at a specific amplitude for the shaper to work. To figure out how this circuit works, let's start from the square signal being low at point B. When that happens, the triangular shaping is in the process of ramping up, and such a signal is present on point A. Because the signal in B is low, transistor Q4 is off, and so the triangular signal on A is free to reach both pins 2 and 3 of op-amp U6.1. Note also that pin 2 receives a feedback signal through resistor R29. In these conditions, U6.1 behaves as an amplifier with a negative gain, and therefore its output on pin 1 presents a negative ramp. At the same time, op-amp U6.3 has pin 10 low because of the low value of the signal in B, and since it is configured as a voltage follower, its output on pin 8 is also low. As a result, op-amp U6.2 has a low signal on pin 5 and a negative ramp on pin 6, thus it emits a positive ramp on its output, which is on pin 7. Similarly, op-amp U6.4 receives that same positive ramp at its inverting input, and therefore it outputs a negative ramp, which is basically a sawtooth. When the square wave on B goes high, the triangular wave on A starts going down. Because of the high signal on the base, Q4 turns on and takes pin 3 of U6.1 to low, and as a result U6.1 outputs a high value, while U6.2 emits a low value. This low value goes into pin 13 of U6.4, and therefore this op-amp brings its output to high. At this point, the square wave on B goes down again, the triangular wave on A ramps up again, and the cycle continues from the beginning. 3 input R35 is used to adjust the shape of the signals by forcing the voltage on U6.2 pin 5 to a max swinging value both on the positive and the negative sides. Lastly, the ramp on U6.2 pin 7 and the sawtooth on U6.4 pin 14 are both adjusted in amplitude through the two voltage dividers R40-R42 and R41-R43, and then each goes through a voltage follower that reduces the output impedance. Let's see all of this on the prototype in lab. And here again is the implementation of the schematic on a breadboard. Here we have the TL074 with its 4 op-amps, the control here, and we have the LM358 which provides the buffering and the impedance adjustment for the two outputs, the sawtooth and the triangular wave. Let's see how this works, so let's connect it to the rest of the circuitry. So let's put all together now. So I'm gonna attach now the connectors for the power supply first. And so again we go here and here, then here and here, and finally on the other side this one and this one. Here we go. And now we have to connect to this circuit both the triangular shape and the square shape. We need both of them to control this shaper. So first I'm gonna connect this between this point here where there is the square wave. Let's see, it's right here, there, and on the other side we have to go to here, there we go. And for the other one we have to go from this point and put it here, and which is the same as that one, that's why I'm doing that, and then this point right here. Okay, I hope I put everything in the correct place. Let's power up. Let's first connect here the oscilloscope probe. Let's start with the ramp and let's power it up. And let's go to the oscilloscope now. And here it is. Here is the ramp. And you can observe right over here. And we can of course adjust the frequency. We can increase it. And note that the frequency for the ramp is double the amount of one of the triangular wave. The period is half as much as it was before. On the other end, if we go down, let me slow this so you can see better. See how slowly it increases. Let me adjust a little bit more. See, we have 2 seconds per square right now, and look how slow is this ramp going up. But that's exactly what we were looking for, because this way we can control things in a nice way on the synthesizer, and we can create all the possible effects. Let's let it go up a little bit more. A little bit more. Now it should come down. Here it is. It drops instantly because of that transistor that causes the cut immediately. Let's take a look now at the other shape, which is the sawtooth right here. And let's look at it on the oscilloscope again. And here it is. Let me adjust the time base so you can see it better. And it's a pretty nice shape. Just for the sake of it, here is the entire circuit of the LFO, complete with all the component blocks. In the next video of the series, we will assemble this circuit on a PCB. We will also put together the whole module and we will install it on the synth rack. We will then test it along with the other modules already present in the rack. It's gonna be awesome! And so, I'll see you in the next video, and as usual, happy experiments!